So great. So let's get started. So today we're going to start a new section on streaming algorithms and how to do sampling within these algorithms. Sampling probably the most powerful single tool you will find in this section. So we'll start with this, and then we'll talk about a couple of few other approaches within the streaming paradigm. So I just wanted to kind of touch base where we are in the class. The last two lectures. So I was not here, of course. So we had some guest lectures. We did not record videos for those lectures. So we don't have the video links, but the kind of the slides that Mesam used are linked off of here, and the slides that Al-Kindi used in his lecture are linked off here as well. So you have access to those. Your data collection report should have been turned in last Wednesday. I've been traveling, was a little sick this week, and I haven't gotten to those yet. I will get back some feedback on those as soon as I can. But if you have questions on the projects as you're going on that, please reach out to me. Happy to provide some feedback as well. And then the next homework assignment, the clustering one, you should have everything you need to complete that. It's been posted online. One student had a little trouble getting access to the data sets. Has anyone else had trouble with that? Okay.
So for part B on question one,
Yep.
want us to implement those algorithms, like if we're going the coding route, can we use libraries like
You can use libraries. I'm not 100% sure it'll do exactly what you want, what I'm asking to do, but you should be following the algorithms we described in class. If you're sure those libraries are doing what you want to be doing, then you can use them. That's fine. Yeah. So it's fine to use libraries. This is your chance to get practice with this. I've tried to set things up so you'll observe the sort of interesting things that you can see with certain data sets. So
you provide a book. Is that the pseudocode for those in there?
I think there's pseudo.
There's a formula for pseudo.
Yeah. So does it have pseudocode? Yeah. 8. Yeah, I think it's. I mean, it's not very. I pass over it. So I think it was after this stuff, hierarchical clustering. I mean, it's like this pseudocode, the same one I covered in class. And then there were two links, two versions that we talked about. And so, there's might be some issues of how you break ties. I don't think there were any ties in the data sets I provided so that you have to deal with. But if you put points on a grid, you'll end up with some ties sometimes. So there should be an order you can deal with it. I mean, frankly, I made it small enough so if you want to do it by hand, it would be okay, right? I more want you to kind of really understand how the mechanism is working and kind of see the differences between the two most common choices, single link and complete link. So if you want to run code and it does it, that's great. If you want to write your own code, it's not too hard to do, but it'll take a little bit of time. Yeah. All right. This should have been in the notes. I linked off the webpage too, but the book has it here also. So, yeah. Yeah. So that's due on Wednesday. I think it's, shouldn't be too much more. I guess this is a little bit confusing. because when you're running Lloyd's algorithm on top of these, you want to have, well, what fraction of the time is it getting the same inputs? And so you kind of, for some of these, I really want you to do a plot, right? And this year I explicitly said, okay, just plot the data without any clustering, just so you're doing that. But when you're dealing with randomized algorithms, you don't get one plot. So kind of a cumulative density estimate of the output is a good way of kind of describing it. And I've hopefully made clear what I'm asking for there. But if there are questions, the TA has office hours today and tomorrow, and I'm available after class and on Canvas and such. So. All right. And there's some kind of questions where it's like, okay, how many clusters do you think there should have been, or which one worked the best? There's not like, okay, a definitely right or wrong answer. I just want you to kind of put some thought into it and engage with it, because in the real world, no one's going to say, oh, you have to run this one algorithm. You're going to say, well, you get to choose that, and then you have to decide which one did the best job. And sometimes it differs based on the data set or the kind of the task that you're trying to do. Okay. Other thing is there is a midterm test coming up that will that will cover everything. Let's see, I think it does not cover the streaming section of the class. So kind of everything up through clustering. I wanted you to be able to finish the homework before we did the midterm, because I think doing the homework forces you to understand it a bit, this a bit better. And I didn't want to have it the day right after break. Felt that may not be great. So we're going to have it the Wednesday after break. It's going to be in class, on paper, be like 3 or 4 questions, and you'll have the whole class to do it. You can bring in a piece of paper that has, what I say, I think front and back. Yeah. One sheet of paper, front and back, and you can write anything you want on it, but you won't be able to bring in the internet, or so you'll be here, the piece of paper. You should not need any calculators. So just a piece of paper with you and pen, and you'll take it in class. This is a practice one that I've changed the material in the exam, what we cover in the class a bit, so the material may not match exactly. There's more focus on K-grams and Jacquard in previous years. So you see another question here, but I think it gives you kind of a representation of what the exam could be like, right? So if you take this and can answer all these questions and think you can do that in an hour and 20 minutes, then you should be fine for the exam. If you think, okay, man, I don't understand that as well as I thought, then you may want to kind of review stuff a bit more. Okay. Yeah.
Where can we find, or what do you recommend for extra questions for this exam?
If you look in the textbook, it has the printed version of the textbook, not the free online version. It has a bunch of questions in it. You can look at there. There's this UBot AI thing I got to link from the Canvas page. You can try playing with that, see if you think that's a useful way to explore learning these concepts. It kind of forces you to talk through it. It'd be good to get your feedback on if any of you have found that useful or not. So that's another way. Yeah.
Just looking at 1B, would we expect something like that on the exam, or should we go ahead and just put that on the 1 page?
It might be good to put it on the web on the 1 page. It may be included, it might not be. So yeah, so yeah, so it's the point is not, I don't want to ask you stuff to memorize equations, but like how to use and think about stuff. So, but Jacquard, I should be able to ask you to compute Jacquard similarly without giving you the formula. That would be reasonable to me. If it was Anberg, which is one we didn't really talk about in class, I shouldn't expect you to remember that one. Okay, I probably wrote Jacquard because I also wrote the equation for Anberg, which is something that I probably shouldn't expect you to remember offhand. That would just be memorization. But Jacquard is a pretty widely used thing that you should know and understand. Yeah. So okay, it's not for the Wednesday after break, so you can ask more questions about it as we get closer to it. Yeah, okay. So we finished the clustering section of the class, which I think is kind of a very central topic. And I think, I mean, I'll just say it again, there's like thousands of different approaches you could take in clustering, and we did not cover all of them. At some point, we offered an entire semester-long class on clustering, and that even didn't cover everything, right? So I think what we covered is the vast majority of what you'll use, but you will also, if you continue in this, you will surely encounter things that we did not cover in this semester. But that's just kind of the nature of the world of data mining and data analysis. It's very broad, and there's lots and lots of topics here. Okay. All right. So with that, we're gonna talk about a new topic, streaming methods, and then we'll talk about sampling within that. And so streaming is kind of a paradigm of studying algorithms and data analysis. And so it's kind of in some sense, it's a model it's a model of computation, where we're gonna be thinking about your input data as going to be A, which is going to be an ordered stream or set, AI. Eventually you get to a N. I want to make sure I use M in the notes. Okay, so they're ultimately going to be M items in the stream, but they occur they're occurring in some order. Okay, so each AI is going to be in some domain. Okay, and for this lecture, we're going to say this is equal to either the real numbers, or maybe it's going to be from some ordered values between 1 and u. All we're going to really want is we're going to be able to add these things together or compare these, and but there'll be other settings as well. But we'll be kind of seeing these things in order. They're all from some sort of domain. They could be more complicated. They could be, there's some customer profile. You're an algorithm that's sitting on a website, and a customer comes and interacts with the website, and you have cookies about the customer, so you know something about them, and you have some interaction that they do. And so this item in the stream is capturing all that information. Okay, so for now, we're going to be talking about much simpler settings, but these can capture much more complicated objects. And later in the semester, we will talk about some more kind of how these can model more complicated objects. So I'm talking about the streaming topics first, because within the dimensionality reduction, one of the lectures will be doing that within the streaming setting. And there we'll have this as a high dimensional vector, and we want to reduce it during the stream. Okay, the other thing about the stream is that items seen in order, so AI before AI plus 1. So you're seeing, so after you don't see A2 until after you've seen A1, okay? And then the other thing is that the memory or space is very very limited. So so it's going to be such that I want to compute something that's going to capture the data and the structure of the full data set A, but I can't store the whole data set A. I have to do this with a very small amount of space. So I want to create a summary of the data set A. So the goal, the goal is a summary of A, but I want with the space is small. Okay, so this will be that the summary will be S, right? This will be the name of this is the summary. And I want that the size needed to store S is small. Okay, so what do I mean by small? By small, I mean that we'll say that this will represent the size of S as kind of the cardinality of S. Think of it as a set, but the size of S is going to be some polynomial of log of M and maybe log of U. Okay, U is the size of the domain that the data is represented in. So if I have, again, maybe this domain is I have 100,000 words. I wanted some polynomial, and maybe it's linear in the log of the number of words, okay, or the log of the kind of the number of items I see. All right. So what does it mean? So this is exponentially smaller than the data size. I should think of log of M as just a counter. Okay. Log of M, what can I store? I have M items. If I have log M bits, I can store a counter up to size M. Okay. So I can store in logarithm of the size of the data set, I can store a counter saying how large is it. Okay, and I could store multiple of these counters, or maybe a polynomial of these. And the log of U, I should think of this as like a label. So if there are U of these items, like words in the world, right, in the dictionary I'm considering, then I can index into one of them and say which word was it. If I want to know which word it was, then I can describe that with log of U bits again. Okay, so it's really exponentially smaller space. I can store some counters and labels and maybe some combination of these things. Okay, so I'm thinking of counters and labels, but I can't store the whole data set. I can't do a counter, say how many did I get of this particular word for all different words. I can't keep a counter for every word. That would be too much space. Or store everything in the data set. I can't store an item for everything I've witnessed. So again, examples of where this has been kind of really useful model is if you have an algorithm that's running on like a router, yeah, where are streaming algos used? Okay, so one is if I'm sitting on a router on the internet. So if you know anything about how the routers and the internet work, that there are a whole bunch of them all over the place, and there are these computers that take packets you send from your computer or the cell tower network, and it has a little header of where it's coming from, where it's going, and then some information captured in it, and it just reads that and decides where to send it to next. Okay, but it has much more limited storage than what passes through. And so it can't possibly store all of the data it sees, but you might want to compute some summaries of all the data routed through that router. What was the properties of the data routed through? It has to be much smaller than the data that passes through the router to store that summary. And at no point can I store something, or can I go back and look at it again. The thing about the streaming algorithm is items seen in order, and you only get one look at them. Okay, so for these, you only get one look, right? So after the router sees the ith item, it sends it on, and whatever it stored or didn't store about it, that's all it gets. It doesn't get to go back and look at it again. Okay, so a router is one application. Another direct application would be kind of a very busy so website. So think of one of the big websites on the web, like Google or the New York Times. There's lots of interactions that users do on the website, and they want to keep track of this and model the users, and kind of in real time figure out what is the statistics of what is going on. But they can't store all of the information, all the interaction, right? When you're on the website, they can see how your mouse is moving, where it's moving over the page, right? If you ever and so how you're scrolling, how you're interacting with it. And they may not store all the information forever, but they want to be able to run some sort of evaluation of how well the website is using, how users, what they were looking at, how they were interacting with it, to kind of understand the traffic, the types of users, and also was the website an effective way of displaying the content. And so there's just so many users interacting with it that you can't handle all the traffic on one machine, let alone kind of keep track of all this information. Okay, so other ways you may not think about it initially is I want to review stores of big data. Okay, so if you look at really historical log files of transactions for long-term storage, sometimes they're even put on tape. One of the cheapest and safest ways to store stuff long-term, at least for a long time. This may not be as true anymore. I'm just not sure, but they would write them on a physical medium tape. You guys probably never used a VCR or like a cassette tape. That's what I grew up with. And so, but they actually store data on these rolls of tape, and they roll them up. And the only way to read them is to unroll them, and you get one pass over it in reading it. And so if you want to review this data, you kind of get to read through it once, and you can kind of go back and forth a little bit if you want to, but you're going to scan through it once. Maybe you can scan through it twice or three times if that makes a big difference. But you may get one pass to read through it. Even if your data is not stored on one of these old formats like tape, if you're storing it on disk or in the cloud, how the data is moved into the memory of your computer is by blocks. Data is stored in big blocks on the disk, and it's moved into memory where it can be operated much more efficiently. And you don't know what's in that block until you go to read it, more or less. So you want to minimize the number of blocks that you're moving from the disk memory into your the disk into your fast memory. And so one way to do that is just say, I'm going to have a streaming algorithm that reads through everything once, and my summary is going to be computed based on this format. And so if you design a streaming algorithm, it will work as a very efficient way to deal with this big data, where you only have to read through it once. You don't have to kind of deal with the thrashing that you can get when the data set you have is bigger than the memory of your computer. Maybe if you did not have enough memory on your computer when you dealt with the large word vector data set, it may have caused your computer to thrash a little bit. When we started with, we went down to, I think, like a 100-dimensional one from 300 dimensions because we were worried it would cause more of your computers to thrash. But if you have a big data set and one way to deal with it is if you have a streaming algorithm that just reads every part once, your computer will not have to do random access, and it will be able to prefetch the next block, and it more or less won't have to deal with these sort of issues. Okay. And then another thing we can think of is these time series algorithms, where we want to do this kind of online analysis. So we're reading data and it's actually coming in one reading at a time. And we maybe could go back and look at it, but we want to maintain a summary of everything we've seen so far. And we're continually updating this every sort of reading, right? So I've worked with some data sets that has these 40,000 weather stations across the US, and they're continually streaming in measures of kind of temperature and humidity and other things. And you want the prediction, kind of the summary of what has been seen up to so far as up to date as possible. You don't want to go back to your stores and recompute it. You just want to maintain a summary over time. So again, there's a time series kind of specific way of thinking about these problems as well. So these are kind of these applications where the streaming algorithms are showing up. And the kind of, it still may seem a bit kind of limited. Why are we focusing kind of three lectures on it? Well, so it really exposes a lot of the main challenges that happens when you deal with big data. The kind of the consistent thing about dealing with big data is that it's hard to do analysis on it. So you really want to have a much smaller kind of summary of the big data. And then you can run a more complicated analysis on the summary that you have that might have some larger polynomial time, or you bring it and you visualize it on your computer, or you do something more interactive with it. But the big data may not fit in the memory of your computer, or you may not be able to visualize everything at once. And so there are lots of paradigms that you can look at. We used to talk about MapReduce algorithms more in this class, which is another paradigm which is kind of has faded away. And there are other things we'll maybe allude to. But the streaming model is kind of the simplest one that really exposes this interface, where you have a very big data set and you want to create a summary that captures everything you care about in the big data set and allows you to do a lot of interactive analysis. It's not the only model for this, but it's really the simplest one to study. And it really is kind of most of the ideas that work in streaming work in these other things as well. I want to identify what is the key thing that I can represent and that I can update efficiently and easily, and captures the essence of the data set. So it's been very pervasive throughout, kind of since this was introduced about 30 years or so ago. It kind of keeps showing up as a really nice thing to study and to understand these big data challenges. Okay. So again, we have a very large data set. We're seeing in an ordered stream. The stream may be ordered adversarially. We don't get control the order, but we want to compute a summary in space that's basically in the order of counters and labels that we can keep track of here, exponentially smaller than the data set itself. All right, so let's start with a warm-up. Okay, so let's say that we have a stream, again, A1, A2, up to AI. and each AI, let's say it's going to be in the set 1, just to make it concrete, up to some value u, right? So it's values 1 through u. Just so I don't have to, I could think of having real values here instead. But how do you store real value? You store it as a float or a double, and like, what do I actually represent? I don't want to worry about that. So I'm going to say that these are some integers up to u. Okay, so I can store a count of them up to size u in log u space, right? So like we talked about before. Okay, and now my first goal, I want to compute the average of the set A. Okay, how do I store in a stream the average of the set A I've seen so far up to time I? Let's say that this is uppercase AI up to the I thing I've seen. How do I maintain in a stream the average of everything I've seen so far? Yep.
So I'd probably need the total.
Okay.
And then you would also need to keep track of how many items there are. So then you can just have 2 double. So 1 double for the current average, and then maybe like just an integer for the amount.
Yeah, and because I said these were integers as input, I can keep actually as integers for both of them, just to make it more concrete in the setting. Yeah, great. So the trick here is I have to keep track of 2 things. One is the total count. Well, see, I'll say that the count at I is going to be the number of A1, A2 up to AI, which is actually just going to be I, right? So I'm just keeping a counter, right? And this I said I can do in log of I or log of M space, right? And then I also have a sum, which is going to be j equals 1 up to I of these values AI. Okay, and both of these I can do an update step, right? The update is C of I gets C of I minus 1 plus 1, and S of I gets S of I minus 1 plus AI. Right, so I can just update the sum and the counter very easily in constant time. And then I don't explicitly store the average, but then I can create the average of A at time AI by just the sum divided by the count, right? And this will equal 1 over I, j equals 1 up to I of AI, right? So I can store the average by storing these 2 different things and always recomputing it on the fly if I need to. Yeah, but if I try to just store the average, I may not know how to update it so easily. Okay. And so note, I can also store the sum of a bunch of things. This would, okay, so this might need, because it's the sum of things that might be up to size u, and I have up to m of them, I might need log of um space, but this should be fine too. I may need to have a very, like a big int sort of day structure, but we won't worry about that. We can figure out how to do that if we need to. All right, this makes sense to everyone? So that these are things I can keep track of. It wasn't just keeping the average, but I could decompose it into the sum and the count. And then I can keep track of the average. Okay, and kind of the variance might be a fun thing to figure out. Can you also maintain the variance in a stream? Okay, it's a little bit trickier than the average. But you can do it by a similar sort of decomposition trick into parts. All right, so that's, okay, so the average is another fairly important summary, but I want to focus for most of the rest of the lecture on doing sampling in a stream. Okay, how do we, and in particular, I want to maintain a random sample S of A of size K. Okay, so I want to have a uniform random sample S of A of size K from the stream. Okay, if I have a random sample, I can estimate the average by taking the average of the things in the sample. Okay, it turns out I can compute the average exactly, but other quantities I won't be able to compute exactly. And I may need to approximate them. And the sample is something that anything that is kind of robust to estimate from making observations of it. If I think I can estimate it by looking at a bunch of observations, I should be able to estimate it from a random sample. So it's an extremely powerful thing to do. It works as a summary for just about everything. It's often not the optimal summary. And so after this lecture, we'll talk about other mechanisms that can have more compact representations than just a random sample. But this should be the first thing you think of out of the box, because it will work for just about anything you care about. Okay. But there are two different types of random samples that I left ambiguous in this statement. Maintain random sample S of A of size K. There are two ways of thinking about this. There is a with replacement. Okay, a with replacement random sample. Okay, this means when with replacement things, I'm pulling balls out of a bin or something like that. And if I could pull, after I pull a ball of the bin, I throw it back in the bin so I can pull the ball again. So this is can draw the same item twice, right? So I could have AI and AI both into S, right? The same item gets put into the summary twice. With this, with replacement random sampling, I get that I get IID. In particular, S is an IID sample of A. So it's each sample, each element of S is identical and independently distributed from the uniform distribution on the set A. Okay, I think we talked about this earlier beginning of the semester. This is kind of the premise of a lot of machine learning and data mining kind of assumptions. So it's a nice kind of property to have. Okay, but it's sometimes a little bit wasteful because I pulled some stuff out twice. Okay, so the other version is without replacement. Okay, random sample. Okay, so this means this one I cannot draw the same item twice. So I can't do it. But it's not IID, but usually you usually gets a better estimate. Okay. If the size of the sample, if S is much less than the size of A, then there is very little difference. Okay, but if the size of the sample, the summary is going to be kind of on the order of the size of A, then this will start to make a difference. I will, as we saw with the birthday paradox, when it reaches about square root n size, you'll start to draw duplicates of these things. And then your sample will start to be kind of wasteful. You'll be storing things that you may not really need to store. This one, the width replacement, is easier to analyze for, I want to say, how well did my algorithm run on a width replacement sample? Because as IID, it's easier to analyze. But this one usually works a little bit better. The without replacement works a little bit better. For instance, if I wanted my sample, for whatever reason, to be larger than the size of the data set, so what would happen with both of these? Would everything work fine with width replacement if I wanted the sample to be larger than the size of the data set? Does this make sense to run? Yeah? Yeah, so the without replacement, it runs out of things if the sample is larger in the data set. But this is, okay, so in one sense, okay, it breaks. On the other side, you draw everything exactly once and you can stop. You have recovered it and there's zero error. You have recovered everything exactly. If the size of the sample is desired size of the sample is larger than the data set, I just say, well, I just retain the whole data set. But with the width replacement, I still have error. I may not have chosen everything. I have chosen some duplicates and I haven't selected everything yet. Remember the coupon collectors, I need about n log n samples to draw everything at least once. So I probably don't even have everything, but I can keep running it even larger. But this one says, well, what's the point? Once I get everything, I can stop. Okay, so this one you can see when the size of the sample gets bigger, this becomes a better estimate. And later when we talk about weights, the improvement with the without replacement with weights is going to be even more extreme. So in some cases, if your size of the sample is really small because you're a really small summary, then width replacement is totally fine, easier to work with, easier to come up with algorithms for, as we'll see, and easier to do analysis with. But the without replacement will do better with larger size samples and when we have weights. It's a little bit trickier to work with and to analyze. Yeah. Well, so the reason might be that sometimes you set some parameter, you say, you calculate ahead of time by doing some analysis, how many samples do I think I need to get a good estimate of this quantity? Okay. And so then I say, I need 100 samples to get this estimate. Well, then while I have a data set, while the stream is coming in, if I've only seen 70 things so far, then what should I do? Should I maintain a sample of 100 things? Well, I shouldn't. I should just keep the 70 things so far and I have it exactly up until that point. Where this one will maintain a sample of 100 things. Some of them, number of them have to be duplicates and I won't have seen everything. So it's a little bit, the algorithms will actually start out in the regime at the beginning of the stream where you have fewer samples than you have things in your data set necessarily. And sometimes you want to just tell your algorithm how many samples to maintain and you want it to run without thinking about this aspect. Yeah. Yeah, okay. So let's start with a streaming algorithm called reservoir sampling. Okay, this is kind of a very classic algorithm in the space. And we're going to do the k equals 1 case to start out with. Okay, so we're only going to maintain one sample. Okay, and we're going to call this reservoir sampling algorithm. And so the idea is that my sample is just going to be a single item, lowercase s. Okay. And so this will be called my reservoir. Okay. And I'm going to keep this reservoir, maintain it as a random sample in the stream. Okay. So this is the reservoir sampling on a stream A. Okay, so initially, call this step 1. We'll say that S is going to get AI, the first thing, the first thing in the stream. A1, the first thing in the stream. So the first thing in the stream, remember, we have A equals A1, A2, up to AI, AM. Okay, so the first item in the stream is going to be put in the reservoir. And then we're going to have a for loop over the rest of the stream for I equals 2 to M. Okay, we have a for loop here. And so I'm going to generate a random value that is uniform on 0, 1. Okay, and I'll say if U is less than or equal to 1 divided by I, then I'm going to replace my reservoir with AI. Okay, and if not, then I'm not going to do anything. And at the end, okay, and then at the end of the for loop, I'm just going to return S. This is the whole algorithm here. Okay, so this is the algorithm. First thing, I put the first thing in the reservoir, and then I cycle through the stream from items 2 through M. And every time I generate a uniform random value, and if it's less than 1 over I, right? So with probability 1 over I select that item and I'm going to replace it and replace the thing in my reservoir with the new item. Okay, and so this is the whole algorithm. Okay, and so this is guaranteed that at any stage in the algorithm, every item is uniformly equally likely to be the item kept in the reservoir. Okay, this is guaranteed to make a and with k equals 1, there's no distinction between with and without replacement here, right? So at each step I, each AJ is with J less than or equal to I is equally likely equals to S. Okay, so it's a uniform random sample is maintained in the reservoir S. Okay, so so why is this true? Why is this true? Well, let's look at the most recently looked at item. When we process this item, AI, it is kept with probability 1 over I, which is what we want, right? There are I items up to that point, and that one is kept with probability 1 over I, which is good. So that's the probability we want to do. The tricky part is we need this to be true inductively for everything we've seen previously in the stream as well. Okay, we can also look at the base case. After one step, A1 was kept with probability 1. This makes sense. After we look at I at A2, it was kept with probability 1 divided by 2, 1/2. And so what was the probability that A1 was kept after the second step? Also 1/2. It was also 1/2 because either A2 was kept or A1 was kept. Those are the only options. A2 is kept with 1/2 by law of total probability. The rest of the probability is on A1, which is also 1/2. Okay. So the tricky part to proving this in general is we're going to inductively say at I minus 1, each AJ for J equals 1 up to I minus 1 is equals to S with probability 1 over I minus 1. Okay, so inductively, we're going to assume that at step I minus 1, this is true. They're maintained with the right probability. Okay, and what is the probability that they are still there after the next step? Well, it's still there if it was, so then it was, if AI was not selected, still there with probability, okay, 1 minus 1 over I, which is I minus 1 over I. So this is conditioned that it was kept before, then the probability it's still kept is I minus 1 over I. It's pretty high. So then the total probability that it was kept would be 1 over I minus 1 times I minus 1 over I, which is 1 over I. Okay, so this is the probability it was kept is that it was kept before this step, which is 1 over I minus 1, times the probability it was not discarded or replaced, which is I minus 1 over I. And the I minus 1s cancel, you're left with the 1 over I. And this is true for any of the things up through the I minus 1th item, the first of these. And we know that the ith item was kept with the right probability. Okay, so this is the proof. Okay, makes sense? It's pretty clever that this little idea kind of allows you to maintain everything with the right probability. So I just have to look at the item, kind of flip a coin with a 1 minus I probability to keep it, and if I do, I replace whatever was in it. Okay, cool. So this works with k equals 1. So now let's do with replacement reservoir sampling. Okay, now k is greater than 1, right? So let's say I want to keep 10 things in the stream. How do I do with replacement reservoir sampling? All right, so this is the IID version. I can keep things multiple times. How do I do this? Let's say I want to keep 2 things. They should be independent of each other, right? They're IID. I could sample things twice if I wanted to, but I don't have to. Not likely to sample them twice, but I could. And they're independent of each other. How would I do for 2 different, maintain a sample of size 2, or in general of size k? I'm going to use the algorithm for k equals 1 case, right? I'm going to use this reservoir sampling algorithm. How would I use it to maintain a sample of size 2?
Restore the first 2 items.
No, well, so I always store the first 2 items. So That would be if I wanted to do without replacement, where I wanted to make sure I didn't sample anything twice. Then if I had two things, I would always sample exactly those two things. But if it's with replacement, then the first sample should not tell me anything about the second sample. The answer is very simple. It's going to be, I'm going to write one line here for the answer.
Just 2 items from the string.
How do I do that?
Just take one out and then put it back in.
Okay. Yes, but how do I implement it?
I don't know about implementing, but isn't the whole thing gonna be uniform distribution?
Yeah, it'll be uniform with replacement. So K uniform samples with replacement, IID samples. If I need to do it in a stream, so I can't go back over the stream. I can't like look at it and then kind of go and look at it again. You ready for me to write up the answer? Yeah. Okay. I'm gonna run K independent copies of the RSA of the algorithm. Right. So I'm going to run the reservoir sampling algorithm with K equals 1 that I have here. I'm going to run K independent copies of it. So they have different randomness. Each of them is going to maintain one random sample. And if I run it K times in parallel, then it's going to give me K random samples. Okay. So they're going to be, so I'm going to run in K. Each one takes constant space, takes constant time updates, right? So if K is pretty small, this is it's fine just to run K versions of it. Every time I see an item, I have K instances of this running. I pass the input into each of them. Okay, might return the same things twice, but that's fine. That's what replacement sampling is supposed to do. Okay, makes sense? A little too easy. Was that maybe? But okay. Okay. What requires a little bit more kind of being kind of thinking about how the algorithm works is the without replacement reservoir sampling. Okay, so now I want to do without replacement, where if there are exactly two things in the stream, I have to pick both of those things. So I have to do that if there are exactly two things in the stream, right? So I cannot pick anything twice. And now I need to modify the algorithm as opposed to just use the algorithm K times. Okay, so let's design this algorithm. Okay, so RSAK. Okay, now I'm going to have K things I'm going to do. Okay, so step 1, and now I'm going to maintain a set S1, S2, up to SK. Okay. So the first thing I'm going to do is I'm going to put in S, A1, A2, up to AK. Okay, the first K things I'm just going to directly put into the sample. Like you said with K equals 2, when I see the first two things, I put them in the sample. This is what I have to do for a without replacement sample. Okay. And then I've got a for loop for J equals K plus 1 up to M. I'm going to do a uniform, I'm going to say U is uniform on 0, 1. I'm going to say if U is less than K divided by I. because I'm at this step, or K divided by, let's make this I here. Oh. K divided by I. So K is now I is now larger than K, so this is a valid kind of probability here. I'm going to do two things. I'm going to remove random S from S, and I'm going to put AI into S. Okay? And then at the end, I'm just going to return the set S. Yeah, I'm not going to try and write that down there. Okay, so this is the algorithm now. Okay, so again, the algorithm looks similar to before, except I'm putting the first K things into the sample at the beginning. Then in the for loop, I have a higher probability of keeping each item. It's now K over I instead of 1 over I. All right, that's the each item is kept with probability K over I individually. And then if I do keep it, I need to remove one of the items at random that has been in the sample so far. Okay, and then after I remove one at random, then I put AI into the sample. So it gets put in the, and S is now called the reservoir. This will be called the reservoir. So I have the have the reservoir. If I flip my bias coin and it's less than K over I, so if K is 10 and this is the 11th item, there's a pretty good chance it will get put in the sample. But if K equals 10 and this is the 1000th item, then it's a very unlikely it'll get replaced. Okay, and then when it is replaced, I randomly kick out one of the things from the reservoir and put this in its place. Okay, and this will guarantee S is a random without replacement random sample of A at any point here. And so the probability, the probability that the probability that AI is in S is going to be exactly K over I at each step. Let's say AJ, that the probability that for all J less than or equal to I, this will be true. So for each item, the probability will be in the sample will be exactly K divided by I. And you can see that at the ith step, this will be true. And with basically roughly the same inductive argument that it will be true again. It's a little bit more complicated because you have to factor in the K and the probability something's removed, but hopefully you believe me, that's true at this point. Okay, so this also is a very simple, easy to implement algorithm and gives you the without replacement version of reservoir sampling. Okay. Let me ask next. Another important approach is weighted sampling, where the stream is A1, A2 up to AM, but it comes with these weights, W1, W2 up to WM. And so now I want to select AJ with probability WJ divided by uppercase WI, where uppercase WI is the sum of J equals 1 up to I this way. Right, so this is the total weights I've seen so far. So I want to sample it proportional to the weights. So this is, for instance, if you remember the k-means plus algorithm, we wanted to sample an item proportional to the squared distance to the closest center that we've selected so far. And this idea of selecting something proportional to kind of some score like this is actually really important for summaries having to do with clustering. And it will also be important for understanding doing like dimensionality reduction. And there's a lot of methodologies where I want to kind of score every point of how much importance it might have and sample it proportional to that importance. So sometimes these weights are defined implicitly based on some sort of criteria. So there are streaming approximations for clustering. They're more complicated than the stuff we'll talk about in this course, but they do rely on the ability to do weighted random sampling. Okay, so this will be a very important key tool for being able to do these streaming approximations for things like for maintaining a clustering of the data set in the stream. Okay, so I'd like to sample proportional to the weights. How would I do this? What if k is equal to 1? So I want to create a single random sample proportional to the weights. Yep.
Maybe you take your weights so you first generate a random number between 0 and 1, and then I would normalize all the weights so that they sum to 1, and then I would just choose the one response, whatever.
Yeah. So what you're describing is how to sample proportional to the weights. So I can normalize the weights. So I can set WJ prime equals to WJ divided by this quantity. And then I can put them between 0 and 1, and I can have these bins that are proportional to these weights, right? This is W1 prime, W2 prime plus W1 prime is here, and so on. And then my random sample will follow somewhere in here. And this corresponds to, this gives me the third, that's the bin corresponding to W3. This is my sample. Okay, so this is a good way to sample proportional to weights, which is if in an offline setting. Okay, but I don't know, this will not work in a streaming setting because I can't make a pass and store all the weights and go back and transform all of them like this. I need to somehow do this, maintain being able to do this in a stream. And this is kind of requires a clever trick. What can I maintain? What part of this transformation is easy to maintain in the stream? Should remind you from the average kind of thing we did before. What were we able to maintain from the average? Yes, good. We can maintain this in the stream. We can maintain in the stream. Right? So we just keep the sum of the weight so far, right? So we can maintain the total weight so far. And we always have access to the current weight, right? So we always know, and we always know WI for processing AI in stream. Okay, so we have lowercase wi and uppercase wi. So what can we do with those two? That tells me the probability we want to sample the ith item, the one we're currently processing, right? Okay, we want to keep, that means we need to keep AI with probability wi divided by uppercase wi. And this is something we maintained in the string, right? So we know we need to keep the ith item with this probability, and we can calculate this, right? So this is basically the only thing we can do. We only want to keep one sample, but if we know if we should keep this as the sample or not. So what should we do if we don't keep this as the sample? Then we keep what was already our sample before, right? And this is exactly the reservoir sampling algorithm, just with weights instead. Okay, so we just do weighted reservoir sampling with k equals 1. Okay, so I do 1, I put the total weight is 0. This will be step 0 for I'm going to maintain S is always going to get AI, and my total weight is going to be initialized as W1. This is A1. Okay. Then 2, I've got a for loop for J equals 2 to M, and I'm going to create a is uniform between 0 and 1. And now I'm going to say if U is less than Wi divided by uppercase W, then if this is true, then S is going to get AI. Okay. And I always update W. Oh, I should have updated W first. J. Okay. And then return S. Okay. So this is the algorithm. All I had to change was I'm maintaining the weights, and I update the weights every step. This should be plus. Okay. And then I decide to keep the item if Wj over W, if U is less than this, right? So now it depends on the total weight so far. This is the right probability. Then I keep this item, and at the end, I just return this item S. Okay, so this is for k equals 1. How about weighted with replacement? So of size k. How do I do weighted sampling with replacement of size k? Yeah, I just do k copies of this, right? I run k instance of this. So run k instances, independent instances of this. Okay. Okay. So now I can do weighted with replacement sampling of size k. Okay. How about weighted without replacement sampling of size k? Okay, that's a little trickier. I actually can't use the reservoir sampling framework anymore. I need to do some other idea, and we're running out of time, so I'm just going to tell you. So weighted without replacement. Okay, where k is greater than 1. Okay, so what I'm going to do is I'm going to have a set that will be a1 up through a k. Okay, and each of these are going to get a value uk, and so u and uj in general will be equal to, actually I'm going to call these p1 through pk. This will be 1 over the weight j times the natural log of uj, where uj is uniform 0, 1. And s, so in the stream, I'm going to say s will be the set of AI with the smallest pi, the set of k these with the smallest values of pi. Okay, so I'm going to assign everything these items, which are going to be called the priorities. Okay, and if I do this if I just want to create an unweighted sample without replacement, I don't use the weights, and I can just use the uniform random value. I don't need to do this natural log transform. Okay, but when I do this, it becomes sampled from an exponential distribution, and the probability that each AI one is in the bottom k weights is proportional to its weight divided by what the sum of the total weights are. So I don't need to maintain the total weights here. I'm just maintaining the items with the smallest k priorities. I can maintain like a priority queue and throw away things after anything larger than the top k. And so I can maintain this pretty efficiently. So I'm going to just keep track of all the priorities, and the ones with the smallest priorities are the ones that I'm going to keep in my sample. And this will guarantee to give weighted without replacement samples for size k greater than 1. Okay, so all right, so these samples are very useful. I was going to talk about how they can approximate something like these one-dimensional distributions, these quantile distributions. Maybe I'll save that for the lecture after break. So we'll talk about another concrete example where we're keeping track of the things called the heavy hitters, the most frequent items in the stream. So instead of continuous items, we're looking for items that appear more frequently than everything else. This was used for like denial of service attacks. When there's one IP address everything going through a router is all going to one IP address. They're trying to send too many packets to flood this thing. We want to detect those sort of instances without knowing which ones they could be ahead of time with very small space. We'll talk about that problem on Wednesday. Okay, and don't forget your homework is due, clustering homework is due on Wednesday as well.